Part 2 of Importance of Codes and Standards. In continuation of our slide, just expand what is code. And one of the, if you really see OD try to explain related to the fabrication industry, it could be conformance of detailed engineering. When we receive order, we try to do the detailed engineering. Detailed engineering may be a detailing of design, detailing of manufacturing, detailing of testing, detailing of overall the acceptance standard for the product or the part, and it could be the final documentation and the way the documentation will be submitted. How do we really differentiate ourselves with the rest of the manufacturing teams or the fabricators, since we are in the fabrication industry and manufacturing industry, and these two industries are going to grow in the coming days? Let's understand what is a good engineering practice. When we say that there are minimum requirements are given in the code, the customer specifies his requirements, but when we are trying to meet those customer requirements or the minimum requirements, I think today's quality standards have improved to such extent that everybody is meeting these requirements or expectations. So we need to do something more. Something more need not be in terms of high standards of quality, because finally it has to be a competitive product. So you cannot really get moon for everything. But what we are following, is it having a consistency? Is it a repeatable process? Can the end product be estimated or end product be predicted? So good engineering is a good methoding, or it's following almost 100% of the standard or the code. And to do that, we have to have very efficient and cost effective processes which will offer the solution for that process. And it should also meet the operational, safety and regulatory requirements. Now let's see the role of a welding engineer in manufacturing. As we understand that welding is the most important process in any manufacturing, as it joins two parts together, and while joining these two parts together, we are going to heat melt the material and bring them together with a welding consumable, which is another alloy, which could be a third alloy if the two parts which are getting joined are of the same material but may not be from the same heat or may not be from the same manufacturing process. One could be a rolled product, one could be a cast product, one could be a forged product, one could be heavily machined product, one could be heavily formed product, or both could be with all these complications and with different materials, different metallurgies. And to join them, then we'll have to use another metallurgy or a combination of alloys by which we will be able to bring these two parts together and give them the required strength and the soundness. So the first, I think the role of a welding engineer is to really understand the physics. Now, what we mean by physics, whether it is a structure, is it a pressure vessel, is it a reactor, a heat exchanger, what is the end use, what is the purpose of this particular equipment, what it is going to really operate for, and for what is the intended service applications and the service lifetime. Second is how it has been engineered. We have choices of materials, we have choices of designs, we have choices of constructions. So which of this choice has been selected, and have we done the fine tuning of each and every part assembly testing sequence to get us the best and effective solution, as we saw in our first or the second slide. Then comes the metallurgy. Now, after having engineered, that means the material of construction is now decided, so we understand whether the part is made with carbon steel, stainless steel, nickel based alloys, cobalt based alloys, aluminium, or is it a titanium or any other alloy like tungsten and all. Then comes in the metallurgy we understand also not only the alloy, but we also understand how it is given a shape and what could be the end result of manufacturing this product in that particular fashion. So this will tell us the grain size, the corrosion properties, the impact properties, the sluggishness of this material, the fluidity of this material, can that be worked in different positions. And then comes the material where the formability, and then machinability, and then comes the welding, whether this alloy can be easily welded or what are all the best options to weld this. The second is to meet the structural requirements. If it is a bridge, you need to have what are the structural rigidity of these parts. So accordingly the joints, the trusses, the overlap, joining of materials is being decided. The process, it can be a carbon steel with stainless steel overlay to get a corrosion resistance. It can be alloy steel with suitable heat treatment to achieve higher hardness or strength. Then there are regulatory, safety, environmental requirements. A regulatory requirement will be that for a boiler it cannot be heated beyond 400 degrees centigrade, or a boiler which cannot withstand more than 200 degrees 200 bar pressure, or what will be the minimum safety factor, or which are all the approved materials to be used in this region of the world. Similarly, from the safety point of view, what are all the operating conditions, if those conditions are going to be getting altered, or we are going to exceed any of those conditions, then what are all the precautions to be taken? Are we going to give some additional stiffening? Are we going to give some additional ventilation? Then the environmental conditions, that means while manufacturing, how this part is required to be manufactured, what are the corrosion protection requirements to be done, how this part is required to be disposed, what can be used. There are certain materials which have a higher percentage of certain alloys which are harmful, so you cannot use them, you have to restrict them. So there are certain requirements which are going to flow like this, and then all this will get translated into design, inspection, testing, non-destructive testing methods and standards and codes. So welding engineer has to learn, understand each of these aspects, and then accordingly look for what will be the right process, what will be the right manufacturing sequence, and according to that, do we have infrastructure, machinery, and if we have, then what kind of a process and consumables we are going to select. And once the process, consumables, infrastructure, machinery is selected, and the above safety and environmental norms are being understood, then we decide on the PPs, personal protective equipment, which are to be used while operating this, or if we have to create a particular environment, a dust-free enclosure, humidity controlled enclosure, Similar to that, we will be doing and analyzing it. Now we have done the basic requirements of it. Now we are going to translate this into the execution. The first step of execution is to train and qualify welding process. Once you get the requirements as per the welding process and the standard which we are following, let's say we are following section 9, then according to section 9 we will be classifying the materials in different P numbers, consumables in different F numbers, and then we will be writing down what parameters we are going to use. If we are going to have impact property, then the supplementary essential variables are also going to get listed. Like we will be writing down the speed, whether it is manual or automatic, and then we are going to then convert this into the non-essential variables, like how we are going to do the edge preparations, how we are going to do interpass cleaning, the placement of beads in layers and passes, then how are we going to dress up the welding, if there is going to be any repair, how are we going to gouge, which process we are going to use it for filling up that repaired portion after gouging. All that will get listed into our WPS, and accordingly additional welding procedures if required are qualified, and then we need to qualify the personnel depending upon the type of joint, depending upon the position in which we expect that particular joint or the number of joints in that equipment are going to come, the environment in which he is going to weld it, the machines on which he is going to operate. So welder and welding operators will get qualified. Then the role of a welding engineer changes. Now everything is set, job is already cut, rolled, machined, drilled, and setup has been done. Now he has to execute the welding, so his role is going to be like a supervisor, supervise the operations, that setups are coming in good condition, the cleanliness is maintained pre and post, and during welding controls are exercised, proper dress ups, and then offer it to NDT to ensure that the joints are defect free. If not, the non-conformance is required to be reported, and the repair activities as permissible by codes and standards is carried out, and then you document all these things. And if there are any non-conformances, not only in the welding but in distortion or in the dimensions, is required to be reported. If fixturing is required, that is analyzed in the stage 2 in the plant to meet the structural integrity. You normally design a fixture, or for a process you have a fixture. If there are 2 nozzles which are required to be exactly 1 meter away, then you have to tie these nozzles 1 meter away and fix it onto a pressure vessel, so you require a fixture. Or you want the tray support rings to be perfectly perpendicular, then accordingly you can have a fixture or a proper selection of a process like double operator technique, and then you choose different positions to ensure that structural integrity is also maintained. However, even after all this planning, in case there are non-conformances, then you choose to look into the root cause analysis, what we missed out in the earlier 4 bullet points, and try to develop that knowledge and document it for the organization, so that next time we have a similar vessel, this knowledge which we have documented, including its non-conformances, is helpful to prevent the possible non-conformances in future. Now that we have understood the role of a welding engineer, let us see if we can organize ourselves properly. And these are the steps. When I mean steps, either we can have a person dedicated for that activity, or a person having 2 or 3 responsibilities, but ensure that these activities are being done. So the first is having a welding engineer's presence at the design office. So when the design office is doing a detailed engineering of our part or of our equipment or sub-assembly or assembly, then at that stage, depending upon the accessibility, depending upon the requirements of the properties, ease of welding, ease of fabrication, ease of handling, the number of subsystems in which we'll be executing the fabrication and then doing the final welding to have a full sub-assembly or equipment. All those discussions are done, the codes and standards are referred, understood. If there are any heat treatments required, if there are any special precautions which are required to be taken on the reinforcement, on the penetration, if these joints are going to become single-sided because of certain fabrication requirements. The next step is to have a welding engineer in planning, as explained earlier. Now, since we have got overall idea as to how the entire welding operations are going to be carried out and proposed welding process, the joint designs have been already identified. Hopefully at this stage we also have got a clarity in the positions in which it will be welded. So accordingly we need to now start planning on the time frame, we need to start planning on the consumables, type, size, specifications, and which are the properties these consumables are supposed to meet, under what conditions we may have certain additional requirements getting superimposed due to our fabrication, like after 2 or 3 shells are welded, then we are going to have 2 surseams, and at that stage, or for a dish stand when we are going to have a long seam, before we form it, it may have a heat treatment requirement which is not specified by the customer, but that's a good engineering practice which we are incorporating to avoid locked up stresses before we take it for the subsequent operations. So like that we are going to really work upon in the planning and decide on finalize the consumable quantity, type, size, specifications and superimposing requirements. Then of course there has to be a welding engineer who will be supervising the training qualifications as explained earlier. And the last is on the shop floor, who will be executing, coordinating with NDT, coordinating with the various other shops to ensure that his output is the right input for the subsequent departments, and similarly ensure that when the assemblies are coming to him for welding or being done the setup, and he has to provide welders for tacking, whether the input conditions for him are the good conditions. That means the edge preparation is good, the angles are good, root face, root gap has been properly maintained, cleanliness has been done, NDT on edge preparation if required has been already done. So similarly the second team shall be into the design team, which will look into the core standards as explained. Planning has been explained. I think I have covered all of it in my first point itself, and this is the way, if really you see this particular chart here. Now let us come, what is the order of importance? I am sure that those who are going to look into this slide for the first time, they are going to jump on me and say that PP, environment requirements, safety requirements are coming the last in the order of importance. The assumption here is that the bare minimum requirements for safety, environment, PPs is already taken care. However, what is coming special from a given equipment which we are going to fabricate now, or a part or assembly, and depending upon its materials, metallurgy, how the environmental conditions, the PPs are going to vary or change. That you will have it only when you have the full understanding. So the first, I think 50 to 60% of this one is required to understand the metallurgy. Unless and until you understand metallurgy, you will not be able to decide on the processes, you will not be able to decide on what kind of structural integrity, dimensional control, distortion control, how difficult, how easy it is, what kind of a fixturing, purging requirements, trailing shield requirements, or the process requirements are going to flow down. So the choice of consumables, environment, if specific environment like discussed earlier, on humidity, on temperature, on dust particles, on overall cleanliness, even using hand gloves like a surgeon or the nurse uses. That means our sweat or any infection which we are going to carry with our hands shall also be not taken towards the weld joints, because that is all harmful for certain alloys. So then comes the NDT, depending upon the NDT, and then comes the fixturing, manipulators, positioners, rotators, the column and boom, or any other automation like Kobo, Robo, and then what kind of a weld edge preparation. This is all going to be discussed in this sequence. First understand the metallurgy, then understand the process and the structural requirements, then go to NDT and understand what kind of defects are acceptable or not acceptable, which are the methods which we are going to follow, and then work on fixturing, and then work on PP. Only when all these activities are done, the welding engineer has really understood and done his job. So this is only the order of importance, the priorities. In case for a particular metallurgy having complex fixturing, like for aluminium, creating a complex fixture being a soft material becomes sometimes difficult. So you have to think, or fixturing itself is not possible. So go back and see, or the need for fixture comes in only when by process, by proper sequencing, we are not able to control the distortion. Then only the fixturing has to really take place. And amount of fixturing also is required to be decided properly. You cannot do extensive fixturing by you have limited accessibility or limited movement, and then you have to do quite large number of start and end points. Like titanium, if you have large number of start and end points, it is not really good. The material is not that accommodative like carbon steel, where you can have as many start and end points, because the flowability, the surface tension, the weightability of this material, like carbon steel, to a certain extent stainless steel is good. But as you go into the higher alloying content, about 5% and above, and nickel, cobalt and titanium based alloys, then the flowability, the viscosity of the material becomes like a honey. It doesn't flow, it doesn't move, it doesn't penetrate by increasing current or voltage. So you have to have that much of gap to really penetrate, or you have to have movement of the torch to really move and spread the material on both sides and ensure that you have a proper fusion. So this way the order of importance has been decided, and we go based on this. Now there are few good to know points in welding. Every weld has shrinkage stress. We cannot avoid, because we are going up to melting point and then trying to solidify. In situ solidification in the weld edge preparation, and that too also it is not uniform all across. As we are progressing our weld, accordingly the weld is getting progressed and processed, so it takes certain time. Welding has three sides: weld composition, the metallurgical properties of the basic weld. Now this being the as welded condition, we need to be really worrying about it. Plus there is the parent metal is going to melt, plus the consumable is going to melt. So the resulting chemistry after anticipated dilution from the parent metal and the burnout of the consumable, we will understand what is the metallurgy which we are likely to get. And if this metallurgy falls into one of the known materials, then the properties will be known. Otherwise, you'll have to really do a testing, understand the behavior, the material characterization. So weld chemistry is very, very important to know. It is not the chemistry of the electrodes or the consumables. It is the chemistry of the resultant dilution which is going to come from the parent metal and the consumables what we are using and the process in which we are using it. The second is the parent metal itself, which is undergoing different heat treatments kind of a thing because of the different cross section from the weld towards away from the weld will undergo different thermal cycles. Some of the cycles will be hardening cycles, some of the cycles will be stress relieving cycles, some of the cycles will be half annealing cycles, some of the cycles will be normalizing cycles. So each of the cycles on that parent metal is going to be different. Weld, as we said, is a cast structure. It's a dendritic structure and behaves much differently than the rolled rod structures. So we must understand as welded properties of the alloy and the selected consumables. Uncontrolled welding, position, process parameters may give a uniform visual look, but will surely have different percentages of non-conformances, defects, or the locked up stresses. So once a WPS is written and accepted, a draft WPS has to be qualified by performing a test called as a PQR. And once a PQR is correlated to a WPS, we shall not change any parameters written in that WPS. That's the rule which we must follow for the critical equipments and even for the normal equipments if you want to have repeatability and consistency. When weld metal is into the molten stage, it has almost 10 to 100 times higher gas absorption capacity. That means if we are using argon, helium, CO2, mixed gases, or we are going to have flux which is burning either in electrode or in a flux cord wire, or we are going to have a chamber in which we are going to do the welding. Each of these gas will have a solubility or the absorption into the weld metal, and this gas is, as I written here, 10 times higher absorption or the solubility. Now, unless and until we give sufficient time for weld to solidify, and while solidification ensure that these soluble gases or the gases which are absorbed into the weld metal, molten weld metal, are released, then only it will not reflect it into the porosity or some kind of inclusions, and such porosities or inclusions may be a trap for hydrogen to get collected, and once this hydrogen, which is the finest particle, gets accumulated there, the pressure keeps on rising in that cavity, and that leads to a very high stress concentration at microscopic level and creates a notch. And if you have highly stressed or highly hardened or high strength materials which has martensite or ferritic structure, this hydrogen becomes detrimental. And if there are service conditions which are going to have cyclicity at higher temperatures or at higher pressures or at higher loads, this entrapped hydrogen gas in this porosities or inclusions, which has already created a small notch because of its high pressure, starts propagating that notch into a crack, and a phenomena called as a cold cracking or delayed cracking takes place. So we have to be very, very careful in keeping all our gases as low as possible and have sufficient time for cooling, so that these are driven away between solidus and liquidus, so that we land up into no defect. The best way to control distortion, everybody knows, is to work along with the neutral axis. Weld either side of the neutral axis, use staggering, use locking directions for every joint, do balancing of the weld deposition on either side of the neutral axis or either side of the joint, choosing the right processes, choosing the right parameters, bare minimum heat input, heat extraction, a good weld edge preparation, control number of passes, layers, position them well so that you have sufficient gap for every pass and for every layer, and document all this, recommend all this into your WPS so that you follow it every time and we get consistent operations or the readings. Hope this second part of our video also you liked it, knowledgeable, and we will keep on doing this kind of videos on welding fabrication to have equipments which are far better than what is prescribed in the code standards, and that's how we will differentiate ourselves from the rest of the world or from the other fabricators and win this global competition. Thank you.